This is group theory, symmetries in 3 dimensions. Well, from before we used the triangle, this time it will be a tetrahedron. Now, as always, our identity is just basically the do-nothing transformation. It maps each point to itself. Now, for each vertex, there is an axis of symmetry that passes through the vertex and the centre of the opposite face. A rotational symmetry about such an axis fixes the vertex that lies in the axis and rotates the opposite face. So A, vertex 1 is fixed, and in B here, vertex 2 is fixed, and in C, vertex 3, and so on. Now, the axis through the vertex at location 1 gives the rotation 1 where 1 is fixed, so 2 to 4, 3 to 2, and 4 to 3. Where 1 is 6, 2 to 3, 3 to 4, and 4 to 2. At location 2, it's 1 to 3, and 2 is fixed, 3 to 4, and 4 to 1. 1 to 4, as 2 is fixed, 3 to 1, 4 to 3. And at 3, and so on. We're just fixing these, and we're going through 4 is fixed. So from this we have 9 direct symmetries, but there are more that are found by composition. Like, for example, here composing the first and fourth here gives this, and as you should know from before, that we're starting from the one on the right and we're cycling through them. That's what composition is, like we've shown before. Now, this is a new direct symmetry. It interchanges vertexes at locations 1 and 4, and interchanges vertices at 2 and 3. It is a rotation by pi about the line through midpoint of the opposite edge joining 1 to 4 and 2 to 3. There is a similar rotational symmetry for the other 2 opposite edges, which is shown here. The rotation symmetries are given here. As you'll see, there are no fixed points on these rotations. To find indirect symmetries, we find a reflected symmetry and compose it with all the direct symmetries already found. For example, here we've drawn the plane straight through 1 and 3, so 1 and 3 here are fixed, so we're just interchanging 2 and 4, which 2 and 4, 4 and 2. Now, composing each of the 12 direct symmetries with the indirect symmetry on the right gives these. 6 of the indirect symmetries, the ones that fix 2 vertices and interchange 2 vertices, are reflections in the plane that passes through an edge and the midpoint of the opposite edge. There is one such reflectional symmetry for each of the 6 edges of the tetrahedron. The remaining 6 indirect symmetries are not reflections, but the effects of a reflection on a point is to fix it if it lies on the plane of the reflection, or interchange it with another point if it does not. And these 6 symmetries do not have the effect on the vertices. For example, the 4th indirect symmetry above maps the vertex at location 1 to vertex at 3, but it does not map vertex 3 to vertex at 1. The other 6 indirect symmetries do not have a simple geometric description. Each of them is the composite of a reflection and a rotation. So that's our symmetries in 3 dimensions.